So, okay, so in the program, we are going to start with the first contribution talks session. So let me, give me a second. So the first talk, let me share the video. Okay, so the paper is, Should I Trust You? Incorporating Unreliable Expert Advice in Human-Agent Interaction, from Tamin Love, Rites Ayoda, and Benjamin Rossman. So, Tamlin, I think you are already here. If so, we are going to give you permission to share your screen in case you need it, and also to activate your microphone. Okay, so be aware of that after the after your presentation. If anyone from the audience want to make a question, well, we have two alternatives. One, it's, well, you can use the chat, which is activated, so you can ask a question, and we will ask about we will ask the author directly at the end. Otherwise, you can raise your hand, and if we have time for more questions, we can also allow you to use the microphone and make the question in a live manner. Okay. Okay, so I think I need to stop sharing. And I'll share with sound now. Yeah, that should be work.
Hello everyone, my name is Tamlin Love and I'm presenting work done with Dr. Ritesh Ayoda and Professor Benjamin Rossman at the University of the Witwatersrand in South Africa. Consider the problem of a frail care assistance robot. Suppose this robot has already learned how to perform certain tasks, for example dispensing medicine, mobility assistance, or calling emergency services, but has yet to learn which tasks to perform for which observation. We can phrase this problem as a single-stage decision problem, where the state is the observation, the actions are the tasks, and the reward could be related to the patient's well-being. It's very important for the robot to learn the correct policy in such a situation, given the high stakes present. If a patient falls, for example, we would want the robot to contact emergency services, not wander off and prepare supper. At the same time, training the robot is complicated by the ethical issues present when training with human patients, and the general data acquisition problems we have with physical robots. We therefore want to learn as much as possible with as little real-world interaction as possible. One approach to tackling this is to incorporate external information in the learning process. For example, a human caregiver could explicitly tell the robot what to do in important states. In the simplest case, the robot can then do whatever it's told to do. To maximize sample efficiency, we could increase the number of experts we have advising the robot. With more experts comes more information. However, introducing multiple experts has its problems. What do we do when two experts give conflicting advice for the same observation? In general, what do we do if the advice we get is wrong? The problems of incorporating multiple experts and unreliable experts have been identified as open questions in this space and are the focus of this work. Now, assisted RL is a large family of approaches, and it's important to specify how exactly the experts and robot interact in this work. Firstly, we are looking specifically at interactive RL, where advice is given throughout the learning in response to the robot's behavior, as opposed to all at once at the beginning, which may be difficult to elicit in some domains. Secondly, we are looking at policy shaping approaches, where the policy of the agent is modified, rather than reward shaping, where the reward signal is modified to shape behavior. Depending on the domain, this kind of advice may be easier to elicit. We also make two key assumptions about the nature of these experts. We assume that the experts are uniformly reliable across the state space and time, meaning that the expert is equally likely to give correct advice for any given state at any given time. With that out of the way, I can introduce our algorithm, CLUE, which stands for Cautiously Learning with Unreliable Experts. At the start of each trial, the environment samples a state. The agent observes this state and selects an action, based on its own policy and on the advice it previously received, and then receives a reward. Afterwards, the experts have a chance to offer advice on what the agent should have done. The agent then evaluates this advice and updates a model of each expert's reliability. Now let's examine some of these components more closely, starting with the model of reliability. We can intuitively think of reliability as a probability of giving optimal advice. A reliability of 0 means the expert is always suboptimal, and 1 means the expert is always optimal. And so we can model this using a beta distribution, and we can get an estimate of the reliability using the expected value. Now let's look more closely at how we make decisions with these models. After observing a state, we must decide on an action. If we haven't received any advice yet for this state, we are essentially acting on our own and must default to some unassisted strategy, such as action value epsilon greedy. If instead we have a single piece of advice for the state, we can use the estimate of the expert's reliability as a parameter, in a similar vein to epsilon greedy, so that with probability of the expected value we follow the advice, otherwise acting unassisted. When multiple experts have given advice for the state, we can use Bayes' rule to calculate the probability of each action being optimal, given the advice and the reliability estimates. Doing this, we can exploit the extra information we get from consensus among experts, and can even benefit from adversarial experts, which are experts that are so consistently wrong that their advice tells us what not to do. After calculating the action most likely to be optimal, we can select this action with the probability that it is optimal, or else act unassisted. Finally, to err on the side of caution, in case our estimates are poor, we can introduce a threshold such that, if this probability is below the threshold, we act unassisted. This prevents an agent from following advice it is not confident about. Finally, at the end of a trial, we update the reliability estimates of any experts that advised us this trial. The agent evaluates the advice using its own information on the environment, such as a Q function, and then updates a count of optimal or suboptimal advice, which updates the shape of the beta distribution. So how does CLUE perform empirically? Well, to test this, we train the agent on multiple randomly generated environments. We compare 4 agents, a baseline unassisted agent, a true policy agent that follows the optimal policy, a naive agent that always follows advice, and of course, CLUE. We also simulate various panels of experts. Each expert has some parameter, rho true, that defines its reliability, so that with probability rho true it gives optimal advice, otherwise giving suboptimal advice. Our first panel consists of a completely reliable expert. Here the naive agent does very well, as the assumption of reliability holds true. CLUE is slightly more cautious, but also benefits greatly from the good advice it receives. The second panel consists of an expert that is always wrong, and here the naive agent performs terribly. CLUE, on the other hand, identifies that the expert is always wrong, and so learns not to follow its advice, performing on par with the baseline. Finally, the third panel consists of multiple experts with a range of reliabilities, ranging from 0 to 1. Here the naive agent's performance is somewhere in between the previous cases, as it sometimes follows good advice and sometimes bad advice. CLUE performs even better than it did in the first case, as it has more advice to exploit and can identify which is good and which is bad. If we look at how the reliability estimates change over time for each of these panels, we see that the reliability estimates converge in the direction of rho true, and that the experts are correctly ranked in the multiple expert case. So, in conclusion, we've shown that a CLUE agent still benefits from good advice, but at the same time is robust against bad advice. It can correctly rank experts by their reliability, and use this information to exploit advice from multiple experts in a mixed panel. Our hope is that this represents a step towards incorporating multiple potentially unreliable experts in real-world interactive learning settings, though of course there is a lot more work to be done in this regard, especially where physical robots are involved.
Okay. Townley, are you there?
Yeah, hello.
Hello, Townley. So I cannot see the screen, Zoom screen now. Just a second. I'm gonna stop sharing in case you, okay, now. Okay, let me check quickly in the chat if we got any question for you. Just a quick reminder, remember the papers are available at our webpage. So you can find that. Maybe we can share the link here as well. Tamli, I have a question for you. Well, thank you for your presentation, for recording your presentation. I wanted to ask you if you are somehow using or reusing the given advice. What I mean is, imagine the expert deliver a particular advice in a particular situation. Is that advice used somewhere or somewhere in the future when the robot or the agent is facing similar situations?
Yeah, so the way we've done it here is the advice is saved and reused every time the agent encounters that state.
And in that regard, how do you deal with the fact of that actually advice, as you mentioned, can be wrong? And therefore, if you save and reuse it, it's going to keep this wrong advice over time, no?
Yeah, so the idea is that over time, the estimates of the expert's reliability should get better. And so because this advice, assuming the expert is consistent, we can say that old advice that we got from the same expert, if we know this expert is unreliable, we can count that advice less.
Okay.
Yeah, I hope that answers the question.
No, yes, I understand. I'm not really sure if there is any other question. Well, not at the moment. And well, given that we have short time for the contribution talks, and we are probably a few minutes running a few minutes late, I want to thank you, Tamlin, for your contribution and for your talk. We are going to move now to the following presentation. Okay.
Thank you.
Thank you very much. Okay.